without further ado, let's get started. And before I even share some slides, Tim, were you wanting to basically share your screen? I think we can kick off with some of the follow-up on the delivered fuels conversation. And I can, if you just want to share your screen, that would be fine. I don't think, if you sent me something, I haven't worked it in yet.
No, I think it's probably just easier than I can kind of, navigate. Yeah, if that's
sure.
fine.
Yeah, go for it, assuming you have to.
Yeah, should I jump in right now?
Yeah, go for it.
Okay, so just refresh for anyone who's not on. Patrick, thank you, McNamara, lead data scientist here at Sealed. And what we wanted to do was we had alluded to, we want to make, just context, we want to make Caltrack OpenEEmeter as inclusive, as accessible as possible, as it is going to be the basis for measured savings programs that are run under the IRA, which should kick off in 2024 likely. And so one of the glaring kind of issues is around, I'm trying to share my screen, is around delivered fuels customers, which is a tricky one, and most people don't spend much time, but they are definitely going to be ripe for weatherization, electrification, and retrofits under the IRA. And we just want to make sure they're not like excluded just de facto out of being able to be part of a measured savings program, because then it becomes problematic. So what we've done is, after last month's discussion where we just kind of went over the high level things, there wasn't much commentary. We went ahead and redlined, and I'll walk you through these. It looks like I can tell, I think it looks like the screen is being shared. It's not that intense, so don't worry. This is not going to be hours. This is just probably a few minutes. And Patrick, I think what I can do is kind of just walk people high level through what these are. Shout out on the call here if you've got comments. Patrick, you can just jump right in if you kind of add some color. And answer any questions, and we can kind of go from there. So that sounds good. So what really all the changes are in section 2 in the data management, but it comes with a few additive definitions. And so one is around, and we can share this after for people who want to, make a red line or whatever. We can just do what's needed with the group. So delivered fuel, gas, fuel oil, or propane that is physically transferred to the site without the use of a pipeline or wire. And be stored in a tank on site. So it's, physically transferred without pipe or wire, stored in a tank on site. We've defined different kinds of deliveries: a fill up, which is just when a tank is completely filled up, and a flat delivery, which is sort of like hey, just give me 100 gallons or give me $100, that kind of thing, which happens. And then delivered fuel record is just the record, the meter reading equivalent for delivered fuel. So I'll keep pausing. Like, any questions on definitions, and they can come later too. It's fine. All right. So we get into data management. We've just said energy consumption data, meter data, or delivered fuel records. Just to add that in, sort of catch all, and I could kind of hold on. Get that a little easier. Okay. So then there's no changes here. We get down. Okay. So now we're in 2.2.3. So billing data is considered sufficient under the following conditions for the baseline. Estimated periods should be combined with the next period up to a 70-day limit. So 70-day limit was the threshold. And what we're saying is an exception for delivered fuel records may exceed the 70-day limit. So just a simple exception. And then we've got 0.3.4 here. So off-cycle reads, which are considered less than 25 days, should be dropped from the analysis because they typically occur because of meter reading or changes in occupancy, like home went for sale or tenants moved in and out. And so we just say exception for delivered fuels, the records may span less than 25 days, as there is no concern for meter issues or occupancy changes. And Patrick, did you have anything to add to that? I think the occupancy changes on this one is because it would be a completely different delivery record for a completely different owner or tenant.
Yeah.
Is that right?
Oil and propane companies get a new account essentially when the ownership changes. So all that we get from an oil propane company is an invoice for like John Smith at 123 Main Street. And if they sell it, then new name, same house, different record.
And the good thing here is You go ahead.
I'd be concerned about that not actually being specified. This just says there's no concern for meter issues or occupancy changes without that background information. That's dubious to me.
In the background. Oh, you mean without without knowing that it's you just can you explain a little more? Sorry.
Without
you want a
knowing,
different name on the account record, right?
yes.
Okay, so maybe we can make a change there that specifies that.
Well, but thinking about this is like essentially saying, but in this instance, you're talking about submitting someone's name and potentially address into, I have no idea about the security mechanisms for how the data is stored, to be honest. But essentially saying that there needs to be some identifying information associated with delivery record.
I don't know that so I think here I'm trying to remember, Steve, you may have this on the top of your head, but I don't think that in CalTrack 2.0 right now, there's anything specified around occupancy changes. I mean, other than like in the hourly model and talking about modeling occupancy. But is there something in 2.0 that basically says, because I would think there's an analogy here, right? I mean, if you're talking about an electric or a normal gas meter, there's nothing in 2.0 that says if there's an occupancy change, you can't make a model. What we've typically done is relied on program qualification criteria. So anytime that Recurve runs a set of projects through CalTrack for a program that we're measuring for almost any reason, there are programmatic eligibility criteria and there are CalTrack eligibility criteria. And if the program feels as though an occupancy change should be a disqualifying factor during the baseline period or during the reporting period, then that's totally a valid thing to include. I'm not sure I would say there is no concern for meter issues or occupancy changes here. That sort of maybe goes a little far, right? So we might want to soften that a bit, but I don't know that we want to create an extra barrier here for delivered fuels that goes above and beyond what CalTrack is already specifying, considering like the program. And just for anybody out there, if you're using CalTrack, just know that, CalTrack as a sort of statistics-based model, you absolutely can model a meter with an occupancy change. There's no reason you can't sort of do that. But there are absolutely concerns that if that happens in a program, your model may not be fully trustworthy. So I would encourage people to pay attention to those kinds of things if you're using CalTrack or any other model for that matter to make a measurement of a program.
I'm perfectly fine with softening it. That eliminates my concern of things not being specified properly. As it's already now, it's less hard line. So it's fine.
And in some ways, what's interesting too is like, often methodologies don't typically include this kind of context. It's almost like a nice to have. So in some ways, it's throwing it off. Like it would just end it at off-cycle reads should be dropped. The context isn't always like written out like that. So in some ways, it's like if we drop the context from both, it would just be like these should be dropped. This is the exception. Some other way to look at it. But I think the context is kind of helpful because why would it matter? And the nice thing about delivered fuels is if you do get 2 records in less than 25 days, it's actually really good it's like better for the analysis. You've got more data. Okay, well, I think thanks for working through that. And if there's any more concerns, we can certainly.
There was a question in the chat about wood and biomass. So we have essentially kind of punted on the wood and biomass. I don't say customers, but just the qualification. for a couple of reasons. One is measurement is not very precise in units, like cords of wood or pellets. Makes it hard to have confidence in what you're tracking and when you're using what over time. Because I can know that someone has, bought 10 cords of wood on December 1st, but what also matters is the supply, the existing balance or supply for me to be able to understand the delta from when they next buy 10 or 12 or 15 cords of wood. And so we've kind of punted in that regard. And that sort of, even setting aside the fact that you have much more variable energy densities from these kinds of fuels than you get from heating oil or propane or natural gas or obviously electricity. And so from our perspective, we work with customers who have these folks have like secondary heating systems, but not as primary heating systems because it's just not reliable to bill against.
I think that all makes sense. I just asked because I also think it's worth being explicit that this is out of scope and it's not in Caltrac, just so that's clear. Anybody reading it?
Yeah, that's a good point. Because we've introduced, sorry to scroll through here, but so we've introduced delivered fuels. Would this be the place to say this does not cover, wood or
Well, it
bio?
does explicitly state a gas fuel or oil or propane. It like explicitly defined those.
Mhm.
Yeah, I know that obviously the people who have wood biomass as a primary heating system, that number is very, very tiny. I don't know if they would be eligible under any program, really.
Yeah.
Like the
I'm
original
more
goal,
just
the
saying
impetus
that
of this was like to qualify for, or make sure everybody could qualify for MSI purposes, but like I don't think we could even measure it in the right way.
it seems like there could be an extra paragraph here saying that wood is not part of this. And if you're looking for wood, it's just not here. Like don't try to find wood and
That's fine.
I'll make a comment. Yeah.
for the sake of doing that.
I think it's fair.
Yeah, it certainly wouldn't hurt anything.
Yeah, no, it can't. Yeah, I think that's good. And I do think the programmatic qualification, what Patrick said and what you alluded to earlier, Adam, would be where that gets kind of taken out because it can't be measured and so probably wouldn't get applied. Okay, so moving on, the next section says for pseudo monthly billing cycles, periods spanning more than 35 days should be dropped. For bi-monthly periods spanning more than 70 days should be dropped. So pseudo monthly, I guess, is sort of, yeah, so anything around 30, 31. So we said for delivered fuels, it would be superseded by the following requirement. And it's a little bit of an if then kind of thing. So if the only use for delivered fuel is space heating, then there must be at least 2 fill-ups that cover an entire heating season. So October 1st to April 30th. If there are non-space heating uses of the delivered fuel, there must be a minimum of 3 deliveries in that previous year, 365 days, and either at least 1 billing period no more than 6 months. And so that time between the 2 deliveries is less than 6 months and encompasses June 1st to September 30th. Or there must be a period of at least 10 days with an average HDD per day value of less than 2. And I'll leave you to break that down, Patrick.
Yeah, so essentially the part one is the simplest, which is that if you only use propane or heating oil for heating, then we need 2 readings essentially to measure what you're consuming over a winter period. Relatively simple calculus of this is what you use between, let's say, September and May. These are all the heating degree days. Like it's a relatively straightforward calculation because there's no baseload component. We just care about the slope, frankly. Things get more complex is when you have a non-space heating use for this delivered fuel. a baseload use, which is almost always water heating, occasionally propane for cooking. So what we need here is a reliable period for baseload to understand what your baseload consumption profile looks like. So we increase the number of required deliveries because we need to know more information about the slope, but also information about this baseline or baseload period. And that's where we talk about the summer coverage here. You essentially need at least one billing period that covers this June 1st to September 30th, which is roughly little to no heating season for that oil and propane users. If it's a short delivery period, something with an average heating degree per day per galley of less than 2, where we can say this is a somewhat reasonable estimate of your baseload consumption. Because at the end of the day, we're trying to get the fixed component, the daily value, and the slope. And so we need periods that can encompass each of those things. I fully expected this section to be that with the most questions. So
Thinking about implementation of this, if there are long periods of time in between deliveries, then I'm wondering how it helps at all to have a 10-day period with an HDD per day value of less than 2. And I would say like the heating degree days are determined by the model itself, right? Unless you use a fixed balance point temperature.
Yeah, this is assuming you've already determined a fixed balance point temperature. We've been using a single number for oil and propane customers in the Northeast, in part because of this reason. But there is a world in which you would try to identify the balance point with the existing data that you have, and then find the degree days over that period.
I guess I'm just a little skeptical of that part B. It just seems a little I guess the reason I'm skeptical of it is I could absolutely see there being a time period that would fall under that like sub bullet or whatever, but it wouldn't actually do you any good.
But Adam, there's validation steps that happen after the model is formed, right? Like the CVR, MSE, and R² thresholds. So this test could run after the model determines what the best fit balance point is. Although I'm frankly not sure that we can do a best fit balance point on delivered. Like it's kind of silly, and it's liable to produce some erratic results. So we may not even want to do. But regardless, you can still run a quality check like this after the model has already done some fitting.
It is, oil and propane customers are decidedly more volatile from that perspective, because they don't follow the typical cadence of monthly-ish reads. This summer period is not surprisingly the period in which there are very few fill-ups. People aren't heating their homes, so they're not trying to get fills in their tank. On average, like the maximum duration between fill-ups for our like 2,000 oil and propane customer data histories is about 6 months. So all of them, vast majority of them, are having these very long periods of time in which you don't have like any fill at all or any information coming through. So it will certainly be more volatile from a fit perspective.
Yeah, I mean, and I think that like the greater volatility kind of falls into this bucket of what's we have no good options with delivered fuels, basically. So, is deemed savings the best option? I would think, I would hope we can do better with a meter-based analysis. And when you have very few data points, you're certainly not going to do a lot better than like a Prism type model like Caltrack 2.0. So, it seems like this is the right venue. If we believe that there's a better chance to get more accurate results and to have program participation ultimately, especially in things like the IRA where there's a meter-based pathway and then there's a modeled pathway. And I think if you're on this call, I'm guessing you're somewhat interested in the meter-based pathway. You have all these, thousands and thousands of delivered fuels customers. It seems to me like the lesser of two evils is to try to actually run a model and measure it at the meter. And these are not exactly super complex end uses, right? It's like space heating, or it's, some baseload consumption where it's cooking or, water heating or something. So like this is, I think it's worth keeping to coming back to that, because it's not like the perfect versus this. It's like a really crappy option versus this. And I guess, but I do wonder, reading this, if there are non-space heating uses of the delivered fuel. I mean, to me, that's a little bit tough, because it presumes you have knowledge of the equipment in somebody's home. And like Caltrack has really stayed away from that kind of thing. And I would think for the delivered fuels purpose, like we shouldn't assume that there's knowledge of something like that.
On that same sort of train of thought, so that's basically sums up to, should there be 2 data points or 3? And 2 is non-viable in my opinion, because you have no estimation of uncertainty at all. So without that, it's perfect accuracy, and I just don't see how we can justify a model that we're fitting a line to 2 data points.
Travis, do you think if there's 3 data points, do you need to specify a temperature independent region? I mean, is this actually a better conversation for Caltrack 2.1, where we don't? I mean, I guess in Caltrack 2.0, there's also the possibility of not having a temperature independent region. You just have the cooling balance point equal to heating balance point. Well, in this case, you don't even have a cooling balance point, most likely, right? It's like purely for heating or temperature independent.
Yeah, this is heating only.
Yeah.
I was going to mention that as well. Sorry?
Well, you could almost have it like we don't really do 2 parameter models typically in Caltrack, right? Just a slope and intercept, where the intercept doesn't really mean a base load. It's just a sloped line, right? And that may be sort of the best here, where we don't really assume any kind of flat area. Because, I mean, I was going to like dig in a little bit to the text of what we're asking for, with like the two deliveries, like both being within that non-heating season area. But I almost like where you're going with this, Adam, which is just like, what if we just sort of disregarded the non-heating sections? We assumed that there's not really a change. I mean, in a lot of these cases, there isn't going to be a change in the non-heating loads that we anticipate, that cooking and clothes drying, or, maybe water heating's changed. Yeah, there's probably some, low flow fixtures that like we should be counting water heating, but what would it look like if we just let it fit a 2 parameter and said it's a slope with no flat section? It's just a slope.
I had assumed that was how this was going to be treated, that we were just looking at a heating degree day model only. If we wanted to do a heating degree day with temperature independent, then 3 data points is insufficient and we would need 4. So to me, it makes most sense looking at this that we're talking about a heating degree day model only, in which case I go back to my previous statement of we need 3 data points for that. Otherwise, you have no estimation of your uncertainty.
And does it matter? I mean, so if we went that direction, would it matter when the data points occurred? I mean, you could, like, if you think about the limiting cases and you had 3 data points, you might have one in, equally dispersed throughout the year, with one of those data points falling in the summer and the other 2 falling on either side of the winter. In the other limiting case, you would have 3 data points that are clustered very close to one another temporally. So what specifications would we need to say, if we're saying that 3 data points is the minimum, then I guess the question becomes, what spacing do you need of those data points without, I mean, I think Patrick and Tim, I'm hoping that what we can get to here is actually something that's a little simpler.
Mm-hmm.
Yeah, ideally. What I will say, looking at, we have a few thousand of these customers. There are not very many, a very small percentage, who only get 1 annual fill up, as an example, which is where the 2 data points would come in, right? So that 3, a difference between the 2 and the 3 is relatively small, in terms of the people that it would disqualify. Most of them have 4, 5 over the course of a year.
Are you guys concerned about, I mean, let's say that you have somebody who got a delivery on, let's say that, the baseline period in your program, the intervention occurs on January 1st, 2024. So the baseline period would be the 365 days before that, right? So January 1st, 2023 through December 31st. What happens if a customer gets, a big delivery, they fill up on December 31st, 2022? Now all of a sudden you're riding the coattails of that delivery on December 31st, 2022 into the baseline period. Is that a concern of yours, or is that kind of does that just fall out in the wash? Because the opposite can also be true, right? Like, you get a delivery on January 1st. I'm just wondering if you thought about that, or if that's a concern.
When we think about the 2 data points, we essentially need 2 data points covering a collective winter. And so in this case, if you're saying that so what I'll say is that Sealed, if we saw that data point on December 31st, 2022, would absolutely use it, because it's information about when this usage occurs, and tells us more information about that. But that does not fit the structure of the very specific 365-ish days, 365.25 days prior to intervention point. So you probably wouldn't, that person would be deemed insufficient under this scenario.
But hearing that, because I see in the chat, I think there's looks like a kind of rally for, hey, maybe we can relax the data points if we increase the baseline period. So the question becomes, so just for theoretical sake, if we change this to whatever, I don't know, 450 days or something like that, or just some number, does that take care of it, or is it overrided anywhere else in Caltrack?
That's a good question. I was wondering the same thing, if other language needs to be changed. I'm also thinking that, if we wanted to do something like that, I have a question about the code as well. Does code need to change? Which may be justified, but I don't know that, I don't think Recurve's in a position right now where we can, we have so much work ahead of us to get Caltrack 2.1 kind of buttoned up, get the documentation and the code out, and then we're hoping to turn our attention to the hourly model. So I'm not sure we have a lot of volunteer hours to devote to updating OpenEEmeter specifically around this. So one of the, as Tim, I think, if it's something that changes the code base, then I don't think we're not opposed to that in any way. Like, we're going to update the code base, obviously, for CalTrack 2.1. But I don't know that like Recurve can just raise our hands to do that. So I just want to make folks aware of that.
Yeah, I mean, one change would be, I don't know if this happens like outside in some kind of data loading script, just to conform to the CalTrack model, that there's a start date associated with each meter, each billing period. But essentially that first read isn't a measurement of energy per time.
Correct.
It's just a reset for the time of the last fill up.
Yep.
Right. So at the very least, you just need to do that in the data loading step, is to just, shift all the dates and throw away the deliver
First
amount
one.
in that first one.
Yeah, because it's essentially just telling you when to start for the next number, the next fill up.
Can I ask, and apologies, I know I came in late, so maybe I missed this whole discussion, and you can make me watch the video if that's the case, but have you talked about the issue of people doing partial fill-ups on delivered fuel and how that hoses this?
Well, we have it in the definitions, but I don't know, Patrick would have to.
It's essentially an estimated bill. That's how we've always treated it, as an estimated bill. And maybe we should be more explicit about treating it that way. That essentially means if you get 100 gallons delivered today, that is an estimated consumption that gets trued up at the next fill of the tank. And so when we think about data points or readings, we're thinking about actual readings or fills, not necessarily about deliveries. So the language below, you see it explicitly says fill-ups as a data point.
So if I understand, you expect that the data file has a flag that indicates whether it was a partial fill or a to the top fill. And then when you say estimated, what you mean is that you basically add that partial fill to the top fill, and you'd combine the periods, and you'd say that's one period with a total consumption.
Yep.
Right. Okay. That's fine.
And do you feel like that's fully specified in this language, or is there more needed to make that clear?
I don't think this language fully specifies it, but maybe I assumed this or read it someplace else and assumed that was how estimates were treated elsewhere in CalTrack, was that estimated bills were combined
Oh,
to the next one.
that could be, yeah.
Patrick, is that because you've seen that in CalTrack? I don't ever remember
That's what
seeing
I'm saying. I may have read it and then interpreted it incorrectly, or read it someplace else and assumed it applied to CalTrack, which is the idea that the estimate becomes part of a longer
Like here, if
period of consumption.
periods are estimated, they should be combined with subsequent periods. So
So we should be explicit in specifying the distinction between fill and flat above. It should specify that a flat should be treated as an estimated period.
Yeah, and maybe just refer back to 2.2.2.2.
So these are good discussions. Do you think the change needs to happen here in the definitions or somewhere else?
I would just reference back to that in the delivered fuels language that you're adding below.
Okay.
Good point there. Yeah, Ethan. Mm-hmm.
On the topic was brought up in the chat of a greater than 365 days, essentially just to account for a lot more variance in consumption patterns or delivery patterns. My interpretation of the 12-month pre-install or treatment date was that its 365-day period before and after was one kind of a simplification that allows you to control for seasonal variabilities without having to make a really more complex methodology. to try to handle those differences, because you would be getting different information and different data points.
Well, having longer than 365 days isn't a problem at all for the Caltrack calculations of savings and normal year and all that kind of stuff, right? You can get just as valid models out of a longer or a shorter model. But I think when we tested some actual data conditions, when we were creating the specifications, we found that, shorter ones were more risky because they could miss some of the heating or cooling seasons. And so you sort of got into a judgment call of like, did we get typical seasons in there? And then the longer ones actually got thrown out because it was more likely that you'd get exogenous changes that happened further in the past. And so you wouldn't get a model that was most indicative of the period directly before the intervention. But I think for something like this, it's a trade-off, right? And what I would also encourage us to think about is when we're specifying this language, we sort of open the door to say, well, look, if you have poor quality data, which is to say relatively infrequent fill-ups, right? So I'm on propane right now. I have 2 tanks out beside my house. I don't use very much propane. I've been like more than a year and I haven't even gotten a fill-up and I'm not that low. And like, I just don't even care, right? But basically I heat with wood. But there's going to be a wide range of how often fill-ups are happening. On the other hand, it's hard to get a lot of history, right? So we don't want to say, oh, you've always got to have like 18 months or 2 years or something. But on the other hand, we want to allow someone who only has 2 or 3 fill-ups in a 365-day period to still be included by grabbing another fill-up or 2 in the past. So I think we want to try to set it up as an or and be like, either we need a relatively dense 365 days, or you can go back a little bit further if that allows you to get over a minimum number of actual reads. And we also should be, referencing back to that whole estimated partial fill-ups section, we need to make sure that we're clear in this section that the number of reads that we're counting are only the number of true reads after we've eliminated and consolidated the estimated reads.
Yeah, we had placed language about it being fill-ups here, but we need to make the distinction that fill-ups is essentially actual reads and the flats are estimated.
Yeah.
On the history, like we have 3,330 customers who have given us oil or propane usage, at least at the time I did this analysis a couple months ago. The average history is actually just over 2 years. We typically get more history from oil and propane customers back in time than we do from our typical oil and gas customers, because electric and gas customers, because you're not restricted to whatever data infrastructure the utility has set up to make available to their customers. Mm-hmm. It's what does that delivery company have on their invoice on file, which usually is the entire customer history. And so it goes back, some cases 10 years. For that stuff.
Could we make this simple and sort of do something like where we just say we need at least, at least 3, and just let me know also if we need to change this to fill-ups, just to be more specific, but we can get to that. At least 3 in the previous 365 days, or I don't know, at least 4 in the last 18 months or 2 years, or, some combination of can we just say like, or just take more time and who cares?
Before we get to that, I think it's a good idea. I have a question for folks to just think about as just popped in my head. In Caltrack, there's typically the concept of a blackout period and it's usually reserved for a project implementation. So, if a project takes 2 weeks to install, then in Caltrack hourly, you say, drop those 2 weeks from either the baseline or the reporting period. Just don't pay attention to those data.
Right.
Is there any potential for modifying the definition of a blackout period when you're considering delivered fuels, such that you can effectively move the window to grab 3 data points minimum, or to move the window to the most, if there's a data point you can grab in the past where it's like, that's when they got their delivery, and you can bracket that with 365 days, keep the 365-day baseline period and keep the simplicity around that, but also be flexible in like where you pull the data from. Just just a thought up. It might be a dumb idea, but
Well,
just
I've thought about it because the way that we qualify customers is we get 12 months of usage and we say at least 12 months of usage just to get an idea of their patterns, right? And then we build a proposal and set up installation, but installation is weeks, sometimes a couple months out. And so there already exists this gap between qualification agreement and then installation. I definitely am open to that discussion. I think the challenge is like because we can go so many months between deliveries, it would be like defining what is like an appropriate time period beforehand. Or if we just say like 4 deliveries in the 18 months before installation, as opposed to like whatever your original qualification history was or what have you, then maybe that works.
Mhm. I mean, so usually in Caltrac, there are tests, there's data to back up decisions. Do you guys feel like there's anything coming out of this conversation that you could test that would help like nail down what should be done here?
So can I give an example of my recollection of something that's sort of similar that we did when we last had this discussion about the billing model baseline period? I think it was something like we set up analysis function to calculate the model parameters and model fit, statistics and stuff like that, such that that function took as one of the inputs how long of a baseline period should be allowed. And maybe in this case, we want to explore length, and then there's a second parameter for like, minimum number of reads or something like that. But basically, you would then let's just take the simple case where we say, X months from the blackout period or X months from the last read, the last delivery before the blackout period. And then run that model for 12 months, 13 months, 14 months, up to 24 months or 36 months, right? And then compare across the population, like what's the, change in some of the error coefficients on an individual premise level as you change that duration parameter. What's the change in slope and intercept if we're allowing it to have intercept, right? So like how unstable does it make the models as we go out longer? So we'd look at a couple parameters like that and basically say like across the population, how much is that changing? And then we might see something like, hey, if you go from 12 months to 18 months, no big deal. 12 months to 24 months, not so bad. You let 36 months in there and holy cow, we've got all these outliers that like, that's when they, changed their heating system was, more than 2 years ago. That's much more likely, or something like that, right? Mm-hmm. So typically we'd hope to see from something like that as we take the same, framework and then change that one parameter of, baseline duration. Do we see any inflection points in the distribution across the population? Does that make sense?
It makes sense to me. I think you would see some meaningful inflection points over time because of the nature of the cadence of these deliveries, which is like 6 months, 5 months, and then 2 months, 1 month, 2 weeks, 2 months. Like you're naturally going to get like kind of high variability there.
And I think because we've got this irregular data series, one of the other dimensions that would be nice to see from doing that exploration of longer duration baseline periods is what is the relationship between the duration and the distribution of number of reads that we have for that total duration, right? So like how much of the population only has 2 and 3 reads at 12 months? How much of the population only has 2 and 3 reads at 18 months? Right? And sort of see like how long do we have to stretch out before we're only losing 5, 10, 15% of the population for a low number of reads. Things like that are also really useful to see, like, what's the what's the relationship there?
Yeah, I would say, Ethan, you are an edge case for us, and that usually folks have at least one, like annually, a fill up.
Yeah,
Usually a few per
I'm
year, because
really,
they
I'm
don't have
really
giant
wood.
tanks.
I'm really wood heat, so I'm I'm a terrible case.
I apologize for disqualifying you in advance with your wood heat. But yeah, I think
Ethan
that
still
analysis
subscribe
makes
to the
sense.
Wall Street Journal only so that he can burn it for heat.
Yeah.
So I
Exactly.
think we can definitely dive deep on what tests could be done, and there's a lot of value in that conversation. I'm wondering if so. I don't want to let the perfect be the enemy of the good here either. What do folks suggest for a way to kind of either resolve this, or are there things that would be good to bring back up at the next meeting? I mean, I feel like we've made some progress here, and we can always refine. I mean, I think one of the things that we want to introduce into the sort of Caltrack process / mindset even is that things can be version controlled, and we don't. The last time we made an update to Caltrack as a group was 2017. I was thinner, I was better looking, I didn't have as much gray hair at that point in time. I think that if we want to go forward with something that we feel like is at least workable in Caltrack 2.1, then by all means let's do it. Having said that, I think it would be there are definitely valid questions on the table. So I'm curious what folks think as like, what is the pathway here?
Well,
my way forward on this is that at its core, Caltrack is a statistics-based model. This should remain as such, which means that we shouldn't expect any outside information, and we should all testing and whatnot should go forward not expecting to get that information. I just mentioned testing, and I said this in the chat, I'll just repeat it, is that I think that we also need to see some distributions by changing the time, the duration of the baseline period, how many data points are actually in there, preferably if you have access to some finer scaled data so that you can downscale it and you can get a better estimation of what the true answer is. As well as including some uncertainty in there so that we can get some estimation of, well, if we specify that it has to be 3 data, the uncertainty is going to be so wildly huge that it's completely unreliable. We need to have some estimation of all of these things.
So would it be like, rather than have 2 and then some caveat for 3, we just say it's at least 3 Phillips in the last 18 months, and you just, I'm hearing from Patrick that like people like that most often we're gonna, that's what we've seen, and we've probably seen more, in aggregate propane and fuel oil customers than a lot of.
I mean, the average duration between deliveries is like 2.5 months, so it's not like the 1 and 2 deliveries per year is uncommon, definitely.
But then we satisfy your thing, Travis, of the 3 points rather than 2, but it's just a little longer period. And
so can I just put a word in here for, I think, what Adam and Travis may to some degree be dancing around in terms of like the data driven decision, right? So let me just like put on an outside perspective of envisioning myself in a year's time, bringing analysis that I've been doing of a bunch of delivered fuel homes, using this new Caltrack specification to a utility with a regulator, and wanting to be able to say, this is a rock solid method. And so don't let, whatever evaluator is looking over my shoulder, tell you that their black box method is better. And I'd love to be able to point to the same type of justification that we have for a lot of the other decisions that went into setting some of these like threshold parameters of, we ran a big data set through.
Yeah, you're saying you have EDA documentation of a large sample set of data. Yeah.
Right. So, and I'm aware that that this request basically lands on your shoulders because you guys have this awesome data set of thousands of homes with delivered fuel, which is not very common, right? Like I've got some data sets I can play with, but none of them are delivered fuels, not with any scale. And so like, I feel like we're circling around an answer that we can live with, right? We've cracked the door open to extending past 12 months. We're considering using a lot fewer measurements than we have with monthly billing. So I feel like, unless there's a lot of folks that are lurking and not contributing who are gonna, yell once we ask for a show of hands for accepting it, that we're on a path to doing this. Are you guys willing to take on that extra work to do some of that data analysis and bring back those statistical distributions? And I'm happy to help brainstorm offline, like separately to give you some feedback on what kind of tests would go into that. And I just know there's a limited amount that I can probably do since it's private data. Are you up for doing that work so that we can reference that analysis?
I think so. Yeah. I mean, it would be me doing the work. So it's not a surprising request. So I think we probably would. I think it's valuable. I mean, conceptually, academically, it's valuable and interesting. I could see that from other people's perspectives, and it's valuable like for our organization because we do work with so many customers who are on delivered fuels that like being able to like get them involved and like participate in the MSI program and these training incentives is great. So yeah, I think generally I can say yes. The timeline is an uncertain question at the moment.
Yeah.
Mm-hmm. Okay, let's leave it there for now, if folks don't mind. I'm glad we spent the time to talk through that, and I hope that it's valuable for you guys at Sealed to get some of that feedback. And so now I'll put ourselves back in the crosshairs here on the CalTrack 2.1 side. Tim, do you mind if I grab the screen?
Oh, yeah. Sorry. So just as next steps, what are we going to just discuss offline about testing to come back with some into this? And the other thing is, do you want me to share? There really was nothing else except like one thing right here, which I think is fairly agreeable. So is that a good next step that we'll talk with Ethan offline about this, or is that?
If you guys are so willing, then I think that would be wonderful.
Okay.
Yeah, I'm pretty sure we have carte blanche to share the anonymized data. So
Okay.
I think we're good there.
Cool. All right. Thanks, guys.
Hey, thank you. That was good discussion. Thanks for the time.
Definitely. Okay. I'm gonna just super breeze through a few slides just to kind of remind us where we're at, and then hand the baton to Travis. So can folks see the deck here?
Yep.
Okay, great. So, all right, really quick. I think what we're looking at here is within the next month, certainly, we are going to be finalizing what we believe a I don't want to say bulletproof, nothing's ever bulletproof, but a solid CalTrack 2.1 fully specified model should be. It's the daily, we're really focusing on the daily model here. So monthly, not really monthly, not hourly, we're focusing on daily. And many jurisdictions have daily gas data, even when they have hourly electric data. So in particular, this set of methods is very important for gas meters. And that's where we think the most improvements also need to be made over CalTrack 2.0, because we see enormous seasonal bias in CalTrack 2.0, specifically within gas meters. So what I'm going to show you just very briefly is where we're landing on some of the problems that we've tried to solve. I'm not even going to cover all of them. I'm just going to like go into seasonal bias and talk for a second about weekend bias. And then Travis is going to talk about some of our next steps. And then I think we're going to be in a position where we have a code base internally that we're going to need to revise in order to get it to a point where others can review it. Right now, it's very much an R&D code base. We're going to need to get it into a format that we can add to the OpenEEmeter and we can have folks reviewing it and things like that. We also need to document everything. So I think our plan is basically to it's going to take us a little while. It's going to take us maybe a couple months to get those steps done. So we're not going to be sort of seeking like final approval, blah, 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 until, we get those steps done. But I think we are circling around a final model formulation at this point. So what are we trying to solve here in CalTrack 2.1? This is the distribution of the fractional bias that occurs during the winter months for residential gas meters. And we're looking at roughly 1,000 customers here. We're seeing that in CalTrack 2.0, the average or the total seasonal bias among this group of customers is negative 7.5%. What are we seeing in CalTrack 2.1, the preliminary model? We're now looking at a seasonal bias of negative 0.8%. So much reduced seasonal bias and a much narrower distribution. So we are very encouraged by this at this point. If we look at the summer, we have the opposite effect. So whereas we had negative bias in the winter, now in the summer we have high positive bias. We still see some positive bias, but it's dramatically reduced. And once again, the distribution is very much narrowed. When just rounding it out, looking at shoulder, we're going from 5.5% to negative 0.5%. So all in all, we're looking at a reduction of seasonal bias, like the average season or whatever is sitting around like 7% seasonal bias, and CalTrack 2.1 is bringing that number under 2%, which is a 75% improvement on this front. We're also doing this with a model that is running much, much faster. Even with the extra complexity of splitting the model by season, using a penalization function to determine what splits are necessary, allowing the model to split by week and weekday, we still have a model that's running 2 to 3 times faster at least than CalTrack 2.0. And if we're only running in like CalTrack 2.0 mode, using the optimization scheme that Travis is going to talk about, we're running about 100 times faster. So this has bought us the complexity that we've needed to add to get to a better performing model. This is sort of what that looks like if you just look at these seasonal bias plots, x-axis, average temperature minus the heating balance point. The 2.0 model, there's a clear mismatch between the observed energy consumption, which is the triangles here in the winter, versus the model. The model's dramatically under predicting, especially right around the balance point. 2.1, that problem is clearly solved. And you can see that in these error profiles here. Similar story for summer and shoulder. The error profiles look different, but everything's, much more sort of sutured up across the entire spectrum of, temperature minus heating balance point. And this is at a population level, these measurements. So if we then look at week and weekday bias, again, this is residential gas meters. This is a bigger problem in electricity consumption, but we can see that these, tails of this distribution where we had really severe like weekend bias, they're just gone now. And so the model is picking out the customers most in need of a split between weekend and weekday, and it's doing this, according to the penalization function. And those tails are effectively gone. So we're seeing good signs in remedying the most severe cases of weekend weekday bias. And I want to say that this is important because this is now an electric meter, and the CalTrack 2.0 model that's generated from weekdays that are, shown here in the closed circles versus weekends, which are shown in these diamonds. The 2.0 model actually gets tricked in this case, and we see this in a number of meters actually, because the hottest data points occur exclusively on the weekdays. And so the model gets tricked because it doesn't know there's a difference between weekends and weekdays and thinks there's a balance point temperature. And this is obviously an artifact of a model that is under specified. So the CalTrack 2.1 model in this case is shown in these orange curves where, again, it has naturally split according to the penalization function, and it's modeling weekdays and weekends separately. You don't have this issue anymore. So I'm going to hand the baton to Travis to talk about how. Travis, I think it's probably best if you share your screen. So let me figure out how to stop sharing. Here we are. Oh, you've already got it. Thank you. Okay, yeah, how about it?
All right, everyone can see? All right, so let's talk about the how. I've talked about all of these things before, but I'm gonna breeze through them a little bit at a high level, but I feel like it's important, since we're kind of reaching the end, that everyone has a good understanding of how things are, not how they've changed and how they're working now. So as far as computational efficiency goes, we are changing from a grid search to an optimization. One way to think about an optimization, my preferred analogy, is basically imagine a mountain or some surface where you are trying to locate where either the maximum or the minimum is. In this instance, it's very easy for us to see that the maximum is going to be right here because we can see the entire surface. However, what if you couldn't see the surface? Instead, you just pick random points and then you see what the height is at those positions. Well, that's kind of what the optimization is doing. And then the height and the location informs the next points, which means that this point, which perhaps is very low or a very high, depending on what you're looking for, is pushing your next choices into the direction leading here towards the center, where in this example we're trying to find the maximum. This is going to be much more efficient than a grid search, where with a grid search you just pick the points in a grid and you evaluate the function, you find out what the height is. And if you wanted, so with this function, you get really close to the maximum here with 9 function evaluations. If you wanted to do the same thing with a grid search, it's entirely possible. It's just going to take 25 evaluations instead of 9. So you can see quickly here how using an optimization is going to get you to a good answer, the better answer, much faster than the grid search. So we've implemented this optimization. And now, as Adam mentioned, if you use Caltrack 2.1 and Caltrack 2.0 mode, it's 100 times faster. Otherwise, even with all of the other complexities that I'm going to talk about, we are still like somewhere between 2 and 4 times faster. Another thing that I've done to increase the computational efficiency is to implement an elastic net. And an elastic net it's a different kind of regression. So in an ordinary least squares regression, Caltrack 2.0, the goal is just to minimize the residuals effectively. Whereas with an elastic net, you want to minimize the residuals, but then you also add in your coefficients. So what does this mean? Like, it doesn't make sense. Well, imagine you've got a plot here of usage over temperature, and we can see here that the best fit is probably a temperature independent straight line. But let's say that the starting point for the model is actually to give some sort of a slope here. Well, it would evaluate this, and then it would do another step, and it would push this down a little bit, and it would see, oh, well, my residuals hardly changed at all. However, I was able to decrease my entire function because I could push that slope value down. So by doing this, you can effectively cut out having to fit a heating degree day, temperature independent, cooling degree day model, and all of the other various subsets. Instead, you just fit one model, and the coefficients are penalized themselves through this elastic net. So we cut out, again, having to fit 4 models, and now we're just down to 1. Much faster. All right, so Adam talked about seasonal bias. This is one example of how that actually looks whenever you're looking at the data from an individual AMI meter, where super common, energy usage on left, temperature on X. So here I show winter in purple, shoulder in green, and summer in blue. And this is kind of like an estimation of what Caltrack 2.0 might try to fit, where it's basically just trying to get, okay, well, this winter is high, summer is high, but I can balance that out with shoulder here. We can see that this is not a good model. It's pretty clear that there's different behavior for different seasons. So we say, if there is a different behavior for a different season, then we should treat that as a different model for a different season. And that's where we introduce this idea of splits, where we can split the season and we fit the model for the individual seasons. And then we have a similar problem for weekday and weekend, where perhaps on the weekends, shown here in diamonds, the usage is very low, close to zero. Let's say it's an electric commercial building of some sort. Whereas during the weekdays, you have your normal behavior with a temperature independent, cooling degree day, heating degree day. Now, the Caltrack 2.0 is going to try to split the difference here, but we can do better. And we can say, let's split based on weekdays and weekends, in which case you would get a model that fits everything much better. So now I've introduced two different kinds of splits. And the naive approach here would be to say, all right, well, we are just going to, for every single meter, the way that Caltrack 2.1 works now is we just split for, so let's say, winter weekends, winter weekdays, everything. So 6 different models for every meter. Well, that's kind of leading us in the direction of everything is being overfit and we're not maximizing our usage of the data in front of us. Instead, we need to go about this intelligently. And for models that everything can be fit with a single descriptive model, I realize I'm using model a lot here. I'm going to change this and I'm going to go with model being the overall description of all of the data, and the submodel is going to be like, for example, this top line here would be a submodel for the weekdays. So we need to basically fit everything so that if one submodel can fit everything, then that one submodel is the model. Whereas if it needs to do splits, then it can do so. Now, we can do a little bit better as far as computational efficiency, because one way to look at this is, all right, so if I just showed you this top plot here of, this is actual data, by the way, of a meter. Again, the diamonds are weekdays and the circles are, sorry, I mixed that up. Diamonds are weekends, circles are weekdays. If you look at this, you might be able to see, well, actually, you might be able to get some information if you cluster off of this. So let's cluster the the seasons, and then if they overlap, I'm going to approach this from the direction of not what splits are possible, but which splits are not possible. So I'm only trying to eliminate possibilities. I'm not trying to generate all of them. Well, let's say that, for example, winter always overlaps with shoulder. It's probably a safe bet then that winter should not be its own season, and it shouldn't be split. You could say the same thing for the shoulder in the summer. However, if we look here at the shoulder months, you can, and we look at the weekdays versus the weekends, there's no intersection between the ellipses. So if there is no intersection, we can say, well, it's entirely possible that there is a split here. And so we can basically, instead of having to calculate all the different possibilities, we can just simplify this down to, well, you need to calculate it as what if everything is one submodel, and then 2 submodels where one of them is for the weekdays and one of them is for the weekends. This cuts down from having to solve for, I think it's 48 different possibilities down to 2. So again, a lot of time savings. We can do better though, because what if the way that we structure those ellipses and whatnot, that they never overlap, and so we're back to the beginning where we still have to calculate 48 different submodels. Well, in that case, one way to look at this is, well, what are the components of these submodels, or of the models that are basically just fitting the same data over and over again? So in this example, I show a full week with shoulders. And depending on how you split this up, like you can combine summer and winter as the other model, or you could keep those separate. But in either case, you still have to fit full week shoulder. So we'll store this information as a component, and then we only have to fit the components that we don't have. Another large time savings method here. Now, on to, I mentioned how we want to intelligently make this system so that it chooses the number of submodels that it needs by itself. Well, to even begin approaching that, we need to start from the direction of experimental design. And the naive approach here is to say, well, we will fit in the baseline, and then we will judge off of the reporting period. The problem with that is that these two things are not the same. And there will be differences in temperature, behavior, any number of things. And this is, I'm not even talking about for participant meters where somebody has had an intervention. Even for non-participant meters, there's still a difference between these two things. So what we need to do is we need to have a method where we can use exclusively baseline data so that we can achieve predictive estimations of our uncertainty for our models. So we need some tools. And I once again bring back cross-validation test train. So imagine that you have your data shown here at the top. One way that you can look at this is, all right, so I can separate out the blue data and I will just fit my model on the red and the green. And then I can, whatever that model spits out, I can judge the error of the test data since it wasn't actually used to create the model. But the issue with this is, what if this test data is not representative of the rest of the training data? What if there's something wonky with it? Well, in that case, that's why we use the K parts. So we, again, combine the blue part with the red part, and now we test on green. And since we do this, in our testing, it was between 5, when I say between, it was either 5 or it was 10. So we did this 5 or 10 times, which means that we've got a pretty representative understanding of what the error is for each of these. And then we can combine all of these in order to get an estimation of the uncertainty as a whole. And this is predictive because all of this is actually based on information where the model was not actually fit on that data, which tells us that in the future, we can also expect similar levels of error or uncertainty. So ultimately, what do we want from this? We want the best model selection, and we want the best, and when I say model selection, I mean the best submodel selection. We want the best slit selection, and we want that information to come from our baseline period where there's no changes and everything can just be judged for it as it is, with the goal being that what we really want from these models, and the super important thing to remember about every one of these models that we create, it's not about how well it performs in the baseline period. What we actually care about is how these things predict the future, because ultimately every single one of these models is used to judge how some intervention has changed things. And so you care about how the baseline period would predict into the future. That's what we care about. Now, with cross-validation, one reason why this is really important, if we look at error on the y-axis and model complexity on the x-axis, if you just keep throwing variables at some data, the training error will decrease. You can fit an in-order polynomial to, what is it, n-1 points, or is it n+1? I can't remember right now. Regardless, you could just fit a squiggly line through everything, and you've got perfect error, 0. But if you actually do the cross-validation that I mentioned before, you'll find that at some point, the testing error is actually going to begin to increase as you're describing noise, and you're no longer describing the underlying functions that drive the data. And so what we really want is to hit this sweet spot right here in the testing data where we've minimized that. On the left side, this is actually where Caltrack 2.0 exists, because there are parameters that it does not see, and so it's simply underfit. Whereas if I were to go all the way to what I described before, where we have every single season and every weekday and every weekend split out by itself, we end up over here on the right where everything is overfit. So what we are after is to hit this optimal region where we have the correct amount of complexity to describe the data that we have. Now, as important as cross-validation is for our development, it is unfortunately untenable to use in the final product because of the computation time. If we were to use it as a final product, it multiplies everything times 5 or 10, and at the end of the day, is that expense worth the accuracy? I would argue not. I think that the cross-validation's purpose is to basically get us to the correct estimation of penalization so that we can get it pretty close to it, but we're also so much faster and we can run this on millions of meters, no problem. So I mentioned the penalization here. So what is that? Well, the penalization is basically that we want to take the sum of squared errors of the residuals of between the model and the observed values, and we want to add some penalty. And this penalty is going to basically describe whether or not we should split, because we calculate all of these. And if you have a lower sum of squared errors with splitting everything up, but the penalty becomes too high, then it ends up choosing the less complex model. Now, there are 4 parameters that describe the complexity. 2 of them are for the submodels. That elastic net regression that I talked about earlier, there's actually 2 things that go into that. One is it's an alpha value, and it's the smaller it is, the less it wants to push those slopes down. And there's also another parameter, but I'm not going to go into it. It's not important. There's also 2 for choosing whether or not a split should happen or not. I have already performed 1 optimization on these 4 parameters, and I have what I thought were my final results until it turned out that I had a bug in my code, and I need to rerun it. It's not a giant bug. Actually, the results that Adam was showing earlier is from the same data set, but regardless, it needs to be double checked. Now, additionally, there are 2 parameters that describe that. I called it a cluster. It's actually a 2D Gaussian. But basically, when I talked about changing the sizes of those ellipses, there's 2 ways to do that. You can multiply the major axis and you can multiply the minor axis. So we're just looking for intersections. So you can basically shrink or grow those multipliers until you hit the point of optimal. And the way that we did this, again, was with an optimization here. We set this up so that it was based on how much test RMSE was lost and how much time was gained. The final question is, should we use the adaptive loss function? Now, I'm not going to go into details. You'll have to dig back pretty far for the last time I talked about the adaptive loss function, because until we decide that, yes, we want to use this and this is the way forward, I just don't want to go into it right now. So what are the best parameters? Well, we are basing this off of a 10-fold cross-validation. The test RMSE, which, as I told you before, is predictive of future uncertainty. And this is all, we used 6,000 meters. So 4,000 of them were residential gas. The reason that we chose this split is because the primary justification for this work in the first place was that we were seeing extremely high seasonal bias on gas data. So I want to weight that a little more than electric. I've weighted that as basically 2/3, with the combined electric being 1/3. And the remaining 1/3 is 1,000 of that is residential electric, and 1,000 of that is commercial electric. So final result, or not final results, but pretty close to final results. Caltrack 2.0 is on the left here. This is showing winter. You can see that if you look here at the model here at the bottom left, you can visually see that it's low compared to all of the data points. And this is at the top represented by the total cumulative error becoming pretty low. If we look at that on the Caltrack 2.1, that is basically resolved. It's 0.1 in this case, and that is because it has fit in its own model to winter. We can do the same thing for summer, where here it's pretty high, and again, it had its own model in this case, so it was split, and we end up with 0. Obviously, if winter and summer are split off by themselves, so is shoulder, so unsurprisingly, you end up with 0, whereas Caltrack is rather high. But, and in total, again, the cumulative error here on the left is absolute value going to be quite a bit higher than here on the right. Now, that was an example where everything was split out. However, that's not always the case. In fact, here's one model where instead of splitting into 3 models, it's split into 3. And yet the cumulative error here is also quite low. Very promising, and this is exactly what we want. In situations where it is unnecessary to have a very complex model, we shouldn't have a very complex model. And that's what we're seeing. So what's left? Everyone can blame Adam. He found a bug, and I have since fixed it, but I need to rerun optimization because of that, which is going to take probably about a week and some more time after that to analyze it. After that, we have outreach and education. We need to write everything up, the process that we went through to get here, the methodology on how things work now, and the results that justify why this is a reliable method. And then we also need to convert everything we have from R&D code to polished code that everyone here can use inside of OpenEEmeter. So to conclude everything, Caltrack 2.1 is between 2 to 100 times faster depending on how you use it. So I'm in 2.0 mode, it's 0.5 seconds per meter. In 2.1 mode, it's somewhere between 5 and 10 seconds per meter. We show 74% less seasonal bias, where previously the average seasonal bias was 7.1%, and the current seasonal bias is 1.8%. We see less weekday and weekend bias, though it hasn't been quantified quite as rigorously as the seasonal bias. We see better CVRMSE. Something I didn't show you or didn't comment about, Caltrack 2.0 gives some weird spikes in the data. I'm not sure why, but it's pretty standard that it's in almost every single model. I don't know why it exists. I also don't care enough to go look and figure out why, because it doesn't exist in Caltrack 2.1. So I don't know why it was there, but problem solved. And having looked at these same hyperparameters on out-of-sample meters, I can say I don't have any statistics to justify this right now, but I can say that from the eye test, the hyperparameters look to be very broadly applicable. So we can just put it out there, and that's what everyone uses. And that is all I have. And 1 minute over.
Thanks, Travis. One quick comment, and it's just on that splitting. Actually, it's worth noting that the majority of meters are not split across all seasons. The majority of meters only have one seasonal split, so there's some combination of summer and shoulder or shoulder and winter or something like this. So as we're using this penalization approach, we're actually finding that most meters don't have to go to the most complex route in order to be modeled appropriately. But they do need to be split to some degree, which Caltrack 2.1 is, or 2.0, as Travis said, is currently underfit in that regard. So I think we're going to present a little bit more on the electric stuff when we have a chance to refine some of our analysis and get these optimized results fully out. Happy to stay around for 10 minutes or so if folks want to stay around and have questions on this. There will definitely be time for people to provide feedback, especially when we get all of this written up. You know, we definitely want people's review of the write-up. We'll want review of the code if people have time to do that. So this is not your last opportunity by any stretch of the imagination to provide questions or feedback. So rest assured. But if people do want to stay, we're happy to stay for 10 or 15 minutes or whatever. If there aren't any questions, we can go on our merry way. Great. Hearing none, want to thank everybody. We covered a lot of ground today. Thank you to the Sealed folks for talking us through delivered fuels and really getting our minds on that problem. I think it's definitely an important one and an opportunity we have. And we'll see everybody next time around.